Hi, my name is Davina. I work as a researcher at Lambda. I work on model evaluations and safety. I basically come from a physical AI and self-driving background. So I did evaluations and safety there as well. I'm going to make a few analogies to that, which is why I call that out. Today I'm going to talk about a month-long security competition that we conducted with the help of Berkeley RDI. Basically, we had teams compete as attackers and defenders on a leaderboard and compete against each other on prompt injection challenges. We're going to talk about how that went, what we found out. So why are we interested in prompt injection? Let's talk about echo leak because that's the sort of production incident that we want to be able to catch before it happens. So what happened here was, an attacker sent an email to someone's inbox. This person didn't do anything. They didn't interact with the email. They just asked Copilot a question. Copilot read this email. It read its embedded instructions, which were harmful, complied with it, and exfiltrated their entire inbox. This is the sort of thing that we want to be able to catch with testing, and it is also really difficult to solve because the root cause is architectural. LLMs process instructions and data in the same channel, and they can't tell when they are getting an instruction that's wrong or ingesting data that's incorrect. So the talk is going to be in two halves. The first half is going to focus on the competition. 22 teams took part, both roles. There was 1 month of live attack and defense. So what changed, what improved, how the arena works, how we built something that we think actually is measuring a real signal and not just noise. The second part is going to dive deeper into the attack corpus. So what do these prompt injection attacks look like? Is there any common mechanisms that we're seeing? So yeah, this is the competition. This is what a multi-prompt injection competition look like. There's an attacker agent. It's given a task and a scenario, and it inserts adversarial text into that task. There's a defender agent that's presented with all of that task and content and the attack, and outputs a structured decision. And there's a judge that decides whether or not there was a successful attack or not. So in this competition, there were, as you can see, we had a public phase and a private phase. In the public phase, we ran nearly 94,000 battles between different agents. And in the private phase, we ran around 18K, so a total of around 112. We're going to focus on the private leaderboard battles, because I think those would be more interesting. And to note, this competition ran entirely on GPT OSS 20B. So any of the vulnerabilities, any of the attacks that we discovered are solely limited to this one model. If we run this on other models, we might find very different results. Here's an example of how a battle goes. This is top of mind for me because I'm working on NeurIPS rebuttals, and I'm sure a lot of you are too. So the defender here is an academic AC. They're provided some context and a score for a paper. The score is 5.3, and it's below the threshold, so it should reject it. But the attacker tries 3 different approaches, starting with like some vanilla persuasion, which failed, then using a system notice injection, which looked like it could have worked, but it didn't because there was no basis for it. The attack that finally worked is when the attacker claimed that there's a data error in the original upload, and they uploaded a corrected assessment, which upgraded any of the scores that were previously present. So this is sort of the shape of what a battle usually looks like, where the attacker sort of learns from what's going on in the battle and gets the defender, manipulates the defender to do something it should not be doing. So one thing that we think is super important before actually talking about the results of the leaderboard is how do we know that you're actually building a good realistic scenario? Like how do you know that you're not just measuring noise? For that reason, we created a rubric to measure what makes a scenario meaningful. The first thing is a scenario should be difficult. So if you run one model against the same model, they should have maybe like a 50% balanced win rate. This scenario should be sensitive. So if you run a strong model against a weak model, it should actually be able to distinguish between the capabilities. And third, you want it to be, you want this scenario to not just be broken in one round, because that's sort of trivial. So using these three criteria, we basically calculated scores to identify bad scenarios and create better ones. An example we show here is one of HR Hack, where the target is like a salary band and a single number. So you don't need a jailbreaker to get this output, because you can basically binary search the answer. Like if the target is 150, you can ask if it's above, if it's below, and basically get to the answer. So this is not a good, well-designed scenario. So we changed this by making it a canary that only the defender knows, but not the attacker. So when it's leaked, it's clear that there's an attack that has to succeed and not just a binary search. So yeah, what did this month show us? So over a month, 20 teams just like battling it out on these boards. The interesting thing we saw is that attackers initially improved, but mainly they flattened, but defenses improved a lot more. The argument here is, for continuous red teaming, what you really want is you want to keep changing the attackers and rerunning your red teaming so that the defender who's living under adversarial pressure can learn more. Second, this is an example of like a winning team and a winning attacker team and a winning defender team, and the different strategies they tried throughout the whole competition. So you'll see that this timeline starts around March 7th and ends around April 1st. You'll see that they start with the baseline attacker and defenders that we provided, but then the red line increases when they added a few more strategies like attacker planning and critique. They also added defending fingerprinting as well as simulating the defender, which by the end gives them the highest score. The defender, on the other hand, mostly focused on leak detectors, payload detectors, and checking if the output itself is validated before sharing with the attacker. The second thing that mattered was the public leaderboard actually cannot see overfitting. So there were, when we ran the private leaderboard, we actually saw that the held out scenarios were harder for everyone. The ASR median dropped around 6.3 points. 15 out of 22 of the teams actually stayed where they were. 4 of them fell really hard and 3 of them did better. Of the ones that fell really hard, we saw that they had pretty like hard-coded harnesses where they conditioned the response according to some hard-coded text and scenarios, and clearly we caught that because we ran a private leaderboard. So the lesson here is don't trust your public eval set, always have a private holdout. Let's see. Now I'm going to talk about the different types of attacks that we saw. Basically, we saw these main 10 clusters, and also I don't see the timer, so someone tell me if I'm running out of time. Okay, so there were 10 mechanisms that we saw in this attack set. The one that was super interesting is cluster 5, which is just ask nicely, because the models don't really understand the difference between a harmful ask and just an ask. If you just ask them for a password, they just give this to you. This was actually an attack that was found in a meta, I think like a meta support chat bot as well recently. Another one that was interesting is C7, which is the findings were wrong. So there's clearly incriminating content in a document, but then you append other content that claims that the previous findings were wrong. And despite knowing that they shouldn't trust the content, the model still trusts it. The third one I think that was interesting was fake pre-approval. So you claim that a VP or someone of importance has approved the action already that the model is supposed to do, and the model just complies with that. The more interesting part to me was that 4 mechanisms transferred across 14 of the scenarios. So just ask nicely, fake pre-approval, findings were wrong, workflow impersonation, they worked across the board, which basically says you shouldn't build defenses around scenario-specific filters. There are attacks that can just work across various classes that you should try to define your coverage with. Here's an example of what fake pre-approval look like. So in this signature forge scenario, the defender is an AP clerk, which reads an expense and approves a cost. There's a 12K marketing event that clearly exceeds the budget of 5K. But this attack claims that the VP has already approved it with some approval code, and that's seen as successful. Similarly, inventory poison is when the defender is an industrial supply agent, and it reviews contracts. And a normal minimum is 200 units, but in this attack, when it's pre-approved, it basically goes 50x its normal and approves an order for 10,000 units. So the point is, these are different domains. There is no similarity between the actual scenarios, but the same attack worked. The second thing is that, even within one scenario, various different types of attacks can work. So if you look at the cross-section of scenario and mechanism, there can be different highlights. Different scenarios will have different mechanisms that work against them, and different mechanisms kind of just transfer across different scenarios. So for this email phish attack, workflow impersonation as a mechanism works, just asking nicely works, and findings were wrong works. What's interesting about this email phish scenario is that it's actually inspired by Echo Leak, and it's the same workflow impersonation is actually the same mechanism that caused that failure. So you can catch these big events in this toy data much ahead of before they happen. And yeah, this fourth finding is a little more interesting to me, coming from the self-driving space, where nearly 10% of the wins have a near identical failing twin, where most of the wording is the same, but maybe 2 or 3 words are different. So for example, in one of these scenarios, you'll see that owner confirmed via mobile app, just adding 4 words made an attack from not successful to successful. This to me is cool because this reminds me of the concept of near-miss collisions, where basically in self-driving, if there's a collision, if you go slightly differently, change your speed, change your angle, very small conditions about the attack or the scenario, then that's the difference between something being a collision and not being a collision. So in summary, what did this month of open competitions show us? The first thing is that defense is approved and attacks sort of flatten. You kind of expect this because a lot of the models are fine-tuned for safeguards. The important thing here is you should still be using these models to red team continuously, and ideally use different types of models, because clearly under adversarial pressure, you can find a bunch of mechanisms that you wouldn't find otherwise. This doesn't replace human red teaming. It's more of a complement to human red teaming. The second thing is, a held out set caught all of the overfitting, so please report a private number for your benchmarks, or always run your own private eval and not just trust the public data out there. Third thing is mechanisms transfer across different scenarios, but also different mechanisms work on the same scenario. And last of all, even if you test one prompt and it fails, that might not mean that you're secure, because even slightly varying that prompt in a different way, adding 3 or 4 more words to it, can actually change how the model perceives it. So test your near misses. Don't just believe failure or success outcomes at their face. So that's it, and I'm going to pass this on to Chuan.
Can you hear me? Good? Okay. You have one more slide, Divina. Divina. Okay. Anyway, so by the way, there's now we have a research grant program. You can basically scan this code. There's a link where you can submit an application form. We offer up to $5,000 cloud credit for developers, researchers, to support your work. We do have a review process. Just to give people a little bit of context here, in the first 6 months of this year, we received about 1,000 applications. We granted like 350 applications. So that kind of scale we are supporting right now. Yeah, feel free to scan this barcode. All right, cool. Now, okay, this is actually my slide. Yeah, I'm going to talk about what happened if we pair cloud code with an experiment tracker. I gave the same talk earlier this morning, more from the research perspective. This one is going to be more from the software itself and what's actually happened behind the scene. So just to recap, this is Gemma play the Tetris game. At the beginning, doesn't know how to play and scores nothing. Then we had Claude watching Gemma play and trying to help it to play better. Over a period of 2.5 days, we were able to improve Gemma from scoring 0 to score 16. And some basic rule here, there's no, the weights are fixed for Gemma, so no fine tuning. This is an auto research project, so no human instruction is allowed. However, Cloud is allowed to change the model setting, do prompt optimization, and inference speed up. And every single game has 13 minutes timeout, so Gemma has to think fast enough. All right, very quickly, what we learned is this is not only about how smart Cloud is, this is really about like being very disciplined with doing research project. Just imagine how human will do research. We have a notebook to write down our experiment notes. We have a whiteboard and a sticky notes for communication and broadcast the result. We also have a sign-up sheet to coordinate the resource in the lab. The similar version for AI agent are a bunch of APIs that the agent can call to use tools. And this is our version of the API. We have open source software called the lab, basically try to approximate everything human do for agents. So this is the back end. So this is the front end of the lab. So basically this is an overview dashboard. You can see in the end, Gemma is able to score 16 points. It takes about 368 experiments to get there. It's been 240 experiments since the last improvement, so the things gets more and more challenging. And the total cost is $1.2 thousand. And like every single auto research project, you'll have this graph shows the improvement, and you can see what is kind of unique here is if you hover your mouse to these record points, you can see there's a cluster of result, and these are different experiments from the same idea. So this shows the performance of an idea varies depends on how you tune the idea. Because of that, we also have a average score for each idea. As you can see, the average score is not going to be as high as the maximum score, but the yellow points, you can see there's a overall upward trend. Now, let's go to the first idea. You have to believe me, there's a Git tree where each idea committed to its own GitHub branch, but I'm just going to dive into a couple ideas here. The first idea is everything starts from scratch. What the lab is trying to do is trying to establish a baseline where basically trying some of the off-the-shelf Gemma models and the different settings and see what off-the-shelf Gemma model can do. The model it tries are like 31B, thinking off and on, and there's other smaller version of Gemma. And along this process, the lab took some notes about the findings. For example, the first notes it took is it started to realize there's a 13-minute timeout here. So it concluded, so latency is a first-class driver of total score, not just placement quality. So it tends to prefer smaller models because it has lower latency. However, a few experiments later, it almost flipped its own finding because it found out latency is not the binding constraint here because most of the game finished in 20 seconds because of the top out. So it's really not about the speed of your decision, it's about the quality of decision matters. Then you draw the conclusion, model inference knobs do not matter. The problem is placement quality, not speed. Then start to move on to the second idea, which is trying to find a way to survive. Okay, let's try to see another idea here, which probably is more interesting. I say idea 5. So this is idea 5. And the idea 5 actually has a milestone. Let's see what's happened here. The milestone says breakthrough, disciplined thinking producing the first non-zero score. So this is the first time the lab actually made Gemma to score. So let's take a look what actually happened behind the scene. We can go back to the code diff here. So this is all the change in this idea branch. You basically change the prompt in a certain way that it says reasoning discipline, critical, you have a token budget. You think before answering, but your thinking must be short and follow this 6 short line structure where Gemma is supposed to first identify the target location plus orientation, then test if there's a hole after the placement, then recommend the sequence of move. Okay, so this is the kind of a instruction Gemma is supposed to follow. Let's see whether Gemma actually follows the instruction. To do that, we can see the entire log. The nice thing about having experiment tracker is you always go back and check what's actually happened behind the scene. So this is the entire trace of that game Gemma played. Let's see. Let's start from right from the beginning. Okay, so this is the beginning. As you can see, the game is sort of like represented as a ASCII code. So it has 20 rows, 10 columns. And let's see how Gemma think about problem. Here, thinking exactly is trying to follow the same template. First, identify C0 to C2, which is these 3 spots, to place the pieces. Then think whether it's going to be a hole. No, the board is empty, so any placement is a flush. Then you recommend the sequence of move to place the piece there, which is left, 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 and hard drop. Then in the next turn, you can see the pieces, the previous piece is put here, the second piece is about to drop. Then how did Gemma think? Again, the target location is C3 to C6, that's here. And check the hole, there's no hole. Okay, let's do it. Then Gemma made a recommendation of the sequence of move. Then you realize, wait, I'm already in the middle of the board, so I don't have to move to right, we just need to hard drop and self-correct it. So having this log allows us to inspect what's actually happened behind the scene, how Gemma actually follow the instruction. With the experiment tracker, you can also view the progress, view the result in a graphical fashion. You can actually replay the game. And with that, you can also see some global statistics, like how long did Gemma play the game, and how many turns, what is the latency for each turn, and how many tokens it cost. So all this sort of metadata helps the lab to optimize the strategy down the road. One more thing I want to show on the UI is, I guess it's tools, sandbox. Yes, as you know, agents, they tend to cheat. So in order to prevent them from cheating, we can set up a sandbox. In this case, it's really about the file access. We have to, all the experiments run inside of Docker, so we have to specify which folders on the host machine can be mounted in the container, and what are the files that are read-only, so Cloud will not touch those files. And this is the place where you can set up a sandbox. Okay, let's go back to the talk itself. That's sort of like what's happening behind the scene. Again, the improvement from 0 to 16 does not come in a smooth fashion, it comes in jumps. I'm just going to walk through some of the things I actually made the improvement. The first thing is, as we said, very early stage, Cloud realized it's better to have a disciplined thinking template, and Gemma follow that. That is the first milestone. Some of the other things that helped is, for example, pick the lowest hanging fruit, where if you see different places, just pick the bar that is lowest and put your piece there. Totally makes sense. And don't be too greedy. the game is designed in a way that if you clear 2 rows at the same time, you got 3 points, which is very attractive. But then after a few experiments, the lab realized Gemma was not able to execute that strategy really well. It's better just to pick the lowest hanging fruit and just take what you have right now. Don't wait on it. At some point, the lab created this playbook, which are the best practice for individual pieces. So Gemma does not need to think, invent the move on the fly. And yeah, don't overthink. This is very important, and it's very important to put this in the user prompt, which is the very last thing Gemma sees before it actually sees the board and start to think and take actions. It's also always nice to have fallbacks. In this case, the lab also had the strategy of put some piece to the left as a fallback and put some piece to the right as a fallback, so it's balanced. You don't put every piece to the same side to pile up the bar. There are also other things that the lab tried that didn't work. Here are some of them. The lab tried to use the image screenshot instead of ASCII as the input because Gemma is a multimodal model. However, it didn't really help because it eating too much token budget. Also, too much thinking and no thinking is not helpful. You need sort of like a right balance, right amount of thinking. On the inference side, the lab did try the speculative decoding and find out it didn't work, mostly because it is the quality of the placement that matters more than speed. However, it did use quantized KV cache. On the prompt side, yeah, as I said, don't try to be too greedy. Play these multiple lines in a row strategy. Basically, just like pick, if you can clear a line, just clear a line immediately. And also there are other things. For example, try to disable rotation at all because rotation is like a hard thing to do to save time, and that didn't work. Yeah, I guess in terms of how to use this software, you can basically pip install it from the GitHub. Then there are 3 commands you need to run. The first command is create a lab workspace where your normal auto research artifacts stored there, and also the database for the lab itself. Then you have 2 commands. The first command is launch the lab service, all the APIs and the front end. The second command, launch the lab agent. This is actually a wrapper on top of your coding agent, like Cloud Code or Codex. And the way to launch this agent inside of a wrapper is allow you to directly talk to your lab API. So I have a little video record showing how to install it and start the first experiment. So this is how you can pip install the software. Then we have a tutorial repo. You can basically clone and reproduce the Tetris study. And after that, I think at some point, you launch the lab init. This is the place to start the workspace. And there's one thing you need to do here manually, which is telling the lab your research goal. Here, we just give some really high-level ideas, maximizing the score that the Gemma model achieves while playing the Tetris game. Then the lab is going to expand it into a proper prompt.md, like all your normal auto research project. And it takes a little while for the lab to expand on this. I'm going to fast forward. Yeah, this is the expanded version of the prompt.md the lab created. As you see, there's a structure, the goals, the background, and all that. All right, with this as a prompt.md, what you can do is optionally create a sandbox. In this case, we do need a sandbox to make a bunch of files read-only. And after that, I really cannot see it. Yeah, here, I suppose I'm just going to be very careful here to move forward. Yeah, here you launch the lab service, the background, back end, the front end. And the last thing you need to do is to launch the The progress bar is hidden, so I cannot see it. Yeah. Then you launch the lab agent. Eventually, it basically, as I said, it's a wrapper on top of Cloud Code, where when you launch the cloud in this way, it directly talks to the lab API, and the code is get instruction API to fetch your own research idea and the project instructions, and start its auto research. After a while, you can see the first experiment is launching. GPU is free, sandbox configured, create a baseline idea, and launching run 1. And it takes a little bit of time. I'm going to fast forward to the end, where you can see here it concludes the first run. The baseline 1.1 scored 0. It top out after 21 paces in 21 seconds, and created 3.1 holes per placement, and some kind of final shape of the board. And it drew a conclusion. The finding is that reframe. The finding is the objective isn't really about latency or scoring tactic. It's about survival. Yeah. So if you keep this the lab running for a few hours, it will start to score. Right. Okay. Okay. Just to close this part of the talk, I guess there's a license we can learn from the science history. The modern science started not because humans suddenly becomes a lot smarter. It started because a bunch of people from Royal Society, including this gentleman called Robert Boyer, they start to exercise a habit that write everything down very precisely, so random people can reproduce it. And this is also very important for auto research agents, because they are very powerful minds, can read a lot and make a smart decision in seconds. However, everything will be lost if they don't write things down in the next session. Yeah, and this is the QR code to get access to this software. All right, thanks.
All right, so for the next part of the talk, I'm going to be talking about some of the work that I was doing. Essentially, the model is not the agent, or what 300 million tokens of agent traces taught us about models and their harnesses. My name is Zach Mueller. I am the head of developer relations over at Lambda. And essentially, back in March, late March, Clem, CEO of Hugging Face, made a tweet essentially saying how we need more open traces data sets, because these models are extremely smart, especially the large models that we can't run at home. And the theory was, if you take the traces of these models and train smaller models off of them, they might be more performant. And essentially, we took the task of, let's see what happens. So the recipe looks fairly simplistic, right? Identify a frontier, preferably open source model so no one gets into legal gray areas, generate some reasoning traces from it, so the reasoning, the actions, and the results, and then train a smaller model off of those traces. Well, then you get into this fun problem of it's not actually about the model, because you can have Opus or you can have Kimi running in Claude Code, Codex, it doesn't matter, because the harness itself dictates how well the model can perform. And a lot of times that answer is not very straightforward. For instance, this is on the terminal to benchmark, and essentially what folks are finding is, take say Gemini 3 Pro, which there's a Google Gemini CLI harness for it. You would expect that on a particular bench like coding, you would use the harness that the model was trained for to be successful. And instead, by changing to a minimal, well-crafted harness, not only could the model outperform by 8%, it was also cheaper by almost $20 to run the eval. And on the flip side of that, GPT 5.5, where we have Codex and OpenAI training these frontier models, Codex was better. It was 5% better. It was also 4 times the cost, because OpenAI could have an incentive of, well, let the model run harder, work longer to get these problems solved, and add that extra 1% boost. That's a valid engineering concern. But what this means is that you shouldn't always just stick with one harness. You should experiment. As another example, Kimi K3 came out last week. And over 26 identical tasks, a particular lab decided to see which harness worked the best by comparing performance, cost, as well as time. To no surprise, the harness that was built with the model performed the best. Kimi code got 21 out of 26, it cost 54 cents, and was almost 300 seconds. Coming in second place was Hermes Agent, which is an open source harness by News Research, where it was almost performant, cheaper, and faster by nearly 2 minutes. And then there were a few other open source harnesses like PyAgent and OpenCode, but one that I particularly found interesting is Claude Code, also scored about a 19 while being 3 times more expensive than the rest of them. This is because Claude Code injects a lot of system prompts into their harnesses. And so a lot of folks like to try out the latest frontier model in a harness that might not work the best because most of its context window is essentially being battered by this system prompt. And so, it is a decision of maybe every harness isn't best for every model, and we might not even know what harness works best, but we have to at least try. Now let's go into what a trace is in particular and just have a central definition of it. So you, the user, will prompt a model to say implement this function, or implement this server architecture, or if you're using Codex, go give me frontier research overnight, good luck. Now, what actually happens inside the agent loop is it'll reason for a while, trying to judge what its next step should be. It'll call some tools, and then come to a decision on have we successfully fulfilled what that prompt was. If not, this will go over and over and over again until eventually the model decides either we have a solution or it needs human input. Now, this matters because if we know how the model behaves, then we could maybe train a model later on these traces to have a better performant model with a smaller total model size. So you could run it at home, run it on a single H100, what have you. The problem was we needed to come to a decision on which harness to use, and we chose Hermes Agent. At the time, it was only a few months old. We had a lot of good partnerships with New Research, and also I personally was using my Hermes Agent at home and not OpenClaw, so I also had a personal bias for this. And so we went with Hermes Agent. Now that's step one, right? Now we understand the world and how it's going to interact with it. Step two is deciding which models that Lambda should go after for generating these traces. And essentially it had to fall into 3 buckets. First was it had to be passively licensed because we didn't want anyone to have to worry about can these traces be used for business values or for fun or even having them on your computer. We wanted to make sure this was freely available to the public and to the community to do what they want. The second part is we also wanted to make sure that we were targeting things that the average person can't run at home. At the time, because this was back in March, state-of-the-art was Kimi K2.5 and GLM 5.1. 1 trillion parameters, 800 billion parameters. Unless you happen to have 6,000 Blackwells sitting at home racking up your electric bill, I assume most of us can't really run this at home. And then along with this, I was paying attention to the capabilities of the models themselves. So at this point in time, GLM was state-of-the-art in coding, but this was the beginning of Kimi and introducing this Kimi swarm paradigm, where in one reasoning chain, you can have multiple chains of tool calling happening independently at the same time, which would be very valuable for these small, fast models to do at once. And so this is, sort of recapping, if we have parallel tool calling, then as an example, we could say hey, let's go build this web service real quick. Great, then your open source model can sit there and at the same time start building the framework for a fast API route, start the unit tests for them as well, and then also keep track of versioning, changes, and whatnot through 3 separate different reasoning traces at once, and you don't need 3 different subagents to do this. Now, how we actually generated the corpus was we had Kimi K2.5 come up with about 7,000 different basic to challenging coding scenarios. It covered anything from computer use to build a basic hello world py file. Then we ran all of these prompts through Hermes Agent with different models at the back end. So that ended up being Kimi and GLM across 184 H100s about over a week. And where we ended up was 150 million traces from each model that were then verified to make sure that the trace actually made sense and was successful. Then it went into one bucket. If it was a failure, that is still useful to learn from, and it went into another bucket. And so essentially, like within the weekend after it got done, we just released it and just saw what the community would do. And what happened is it was actually very successful by our book. So this is current. It has about like 380 likes on Hugging Face and about 3,000 monthly downloads. This got up to about 10,000 during the first month that we released it. But most of all, we saw an interesting trend of models that were trained based off of the traces. Quopus is a very common model name, and essentially it is a Quen model trained on Opus traces. And so you end up with this Quopus model. But essentially we were finding that in the size ranges, folks were training these things from down to 1 billion parameters to 27 billion parameters to have a performant autonomous agent at home that can be your assistant without needing to have like thousands of dollars of hardware to get that done. And also we saw particular camps of models being trained. So like first was Quopus, right? So that's Quen 3.6. And specifically, these were all non-mixture of expert models because in general, folks were finding that when you get down to this small of a model size, MOEs tend to matter less than having the larger performant models when speed isn't per se a factor when your agent can run at home and you don't care if the problem gets done in 12 hours or 2 because it's just passively doing its thing. We saw a few interesting experiments where folks would take like the Kimi traces specifically and try and bring this parallel tool calling into extremely small models, like Liquid's LFM 1.2 billion. Sometimes it was successful. I still think like 5 to 10 billion is the minimum to where you can have these more complex sort of tool calling capabilities, but it was a very good effort, as well as some other good Hermes specifically trained models that were designed to work with this harness. Harmonic Hermes ended up being one of the more popular ones, along with Quopus, where their two models combined had almost 500,000 downloads and are still getting models today. And so essentially what I want you to walk away from this talk is not per se, you know, oh, you need to go distill traces and go train your own model. I challenge you to take the models that you know and love and the quirks that you love and hate about the harnesses you use and take these models and shove them into a different harness and see how it reacts and behaves. It might have an entirely different personality because you don't have a 20,000 character system prompt guiding it and the model can be more expressive. Or you might need to tone it down a bit because Codex is so strong that it needs to be wrangled and not just let loose. But if anything, I hope that you can take away this thought of, well, maybe if I use Codex every single day, what happens if I give it Pi? What happens if I give it Hermes agent? And just play with this idea and start to widen your scope of maybe one harness isn't always perfect, even if that harness comes from the place where the model was trained. Thank you very much.